is another part of the regenerative agriculture series or whatever that we've been doing over time. In this particular one, we're going to be talking about getting carbon into our soil. And in a second, I'll tell you exactly why we want to do that. And we'll probably actually stay on carbon for a little while. I may intermix it, or we may come back to it, the different ones that we're going to do in there. And I'll talk about that afterwards. Never mind. I don't want it on video. Sorry, guys. Can't see that. Anyway, so this is what we're going to be doing. So and we're going to do a little bit of a refresher course. Not so much for y'all, because y'all didn't get last month's. We ended up doing it a little differently than what I did, and we had something special for y'all last month, so we didn't do it. It was in the one we did was in Pitkin, was part of this, and we expanded upon it. Anyway, so what are the basics for a plant to grow? Well, there's 4 of them: good soil, sunlight, clean water, fresh air. Kind of self-explanatory, but it goes a lot deeper, because good soil, what does that mean? You know, over time we'll look at it and see. Sunlight, yeah, okay, that one's pretty straightforward. We don't have much control over that. Clean water, yeah, we can have some control. And actually, there's some nuances in this that I've been studying about, and when we get to this part, is actually kind of very interesting. And we'll talk about some things about what they call structured water, which is a total misnomer, but it's actually electrically enhanced water, and then fresh air. And everybody knows what fresh air is. It's non-polluted air. It's in short supply nowadays. Anyway, so dry matter breakdown of plants. Okay, I don't know how many of you realize, but that a plant is 45% carbon. That's almost half of the plant is carbon. And however, we'll see in a minute that we don't ever add carbon to as a fertilizer. We always add NPK, you know. So, but anyway, but even in that, 42% of the plant is oxygen. 6% is hydrogen. Those 3, if you were to grade yourself, you got a high B or an A minus. All right. But when we start adding the rest of it in, nitrogen, it's only 2%. That's one you hear about all the time. Only 2%. Potassium, 1.5. Calcium, the mama of all the nutrients, is 1%. Magnesium, the dad, is 0.4. Big mama, little dad. Phosphorus, 0.3, sulfur 0.2, and all the trace minerals are 0.1. All of these things are necessary for a plant to grow, but if you miss out on these 3, you're going to have a sickly plant. And so we're going to start looking at this one to see how we're going to get the best way we can get that into it. So what about my NPK? What about my nitrogen, potassium, and phosphorus? How much of the plant is that? Well, it's less than 4%. That's not a whole lot, but it's extremely important because things don't work. For instance, a chlorophyll molecule has a bunch of hydrogen, carbons, and oxygen surrounding a nitrogen atom, a nitrogen atom. Without that nitrogen atom, you don't have chlorophyll. So there's some very important things that happen with nitrogen and the potassium and the phosphorus into the plant. So, why is fertilizer always NPK? Well, they're important, and you sure can tell when you add high nitrogen fertilizer because your plants turn green. And you get these nice, pretty green leaves and stuff. But it also could be that big industry can manufacture and sell these things to you. Most NPK fertilizers now, your 888 or 36, 36, 36, whatever type fertilizer, is made from petroleum. It's actually not made from anything organic. It's all inorganic. All right, so I'm not saying that you don't use fertilizer, but you should very, very closely look at if you need the type fertilizer you're putting and the source of that product. Yeah, I had Mayhem go in there and smell it all to make sure it was good. But we'll actually kind of talk about that kind of stuff on another day. But for right now, it's a good little thing to kind of keep in mind is, do I really need this? Is it really in my soil, or do I need to adjust something else to get good NPK? So, right now we're going to talk about carbon. And this is a model of a carbon atom, not an exact model, this is the old school model. And you'll notice that there's 4 electrons in the outer ring, the outer shell, we call that. And that's kind of unique in the atomic world, because it gives it the possibility to have these things called valences, which is the electrical charge of the atom, which allows it to connect to other atoms. You want to have one of a lesser charge going to a higher charge, or a higher charge going to a lesser charge, and that could be negative and positive. Well, carbon is unique is that it can appear negative or positive depending on the situation. It kind of flip-flops, okay? And I guess it would be a trans element, okay? I'm not sure what you would call that, but anyway, it can go either way. So, it's a bi-element, there you go. And so, anyway, so this is what it is. What this makes it do that. This is the basis for a whole group of, or a whole discipline of chemistry called organic chemistry. They probably ought to call it, Al, wouldn't you think, carbon chemistry? So pretty close to it, because everything in organic chemistry is centered around this and oxygen and hydrogen, okay? But primarily carbon. Without carbon, you don't have it. You don't have us without carbon. We're carbon-based too. All right, so carbon and salt. So over the next few sessions, we will be going to be looking at getting usable carbon, that's the key word, usable carbon, into our soils. You had a question?
No, I don't.
Oh, okay. I thought you raised your hand, but that's okay. Anyway, so we're going to try to get usable, because we can put carbon in our soil. I could dump some charcoal in there. That's carbon, you know. But the plant's going to look at it and say, what do you want me to do with this? Kind of like when I gave my dog, you know, this bone that had been left outside for months, and he looked at it and he goes, what you want me to do with that? You know, there ain't nothing there to eat. So that's the kind of thing that you want to do, is we need to have usable carbon in the soil. And we're going to look at how to do that and where the things come. So how does carbon get into the plant? How does the plant get carbon? 99% of it comes from carbon dioxide. From the atmosphere, that's where most of it comes from. From the soil respiration, which we're going to look at soil respiration in a second, because it's really, really cool and really, really key. And from being dissolved in water, because sometimes you'll get carbon, if you have air in presence in the water, sometimes there's carbon dioxide also in it. You got to watch it. You put too much carbon dioxide into water, you end up with carbonic acid, which is kind of bad for plants, so you got to be careful with that. From bicarbonates also in the water. 1% of it comes from microbial transfer at the roots, and carbon compounds also dissolved in the water. So only 1% comes from the roots. The roots are not designed to suck up carbon. So why are we putting carbon in the ground? Why are we worried about that? We'll look at it in a second, but primarily what we're doing is we really want CO2. And we need carbon in the ground in the form of CO2 and other carbons that, carbon compounds that microbials can turn into CO2. So, is it the same? So, carbon, it's in the air that we breathe, carbon dioxide. And the air at sea level contains 420 parts per million, or 0.042%. Less than 1/10 of 1%. Actually, it's a half of a tenth of a 1% at sea level. That's at the ocean surface. For optimal plant growth, you need 1,200 parts per million, or 1.2%. There's not enough carbon dioxide at the ground to feed plants what they need. So how does the plant get it? Well, and here's where it shows this. This is interesting. You have 420 parts per million up in the top part of the plant. Now, the only place that a plant can get CO2 is from the underside of the leaves. Okay, it sucks it into these little things called stomata, and it sucks it in and goes into the plant. Then it's used by the chlorophyll to make sugar.
Yeah, the plants don't breathe from the top, they breathe from the bottom. This makes sense why.
Yep.
You already know about carbon dioxide.
Yep. So, at right just below the surface level, there's 2,500 parts per million. So we got enough there. You can have up to 10,000 parts per million around the roots, but remember, it doesn't take it into the roots. And in very active microbial soil, you can have 30,000 parts per million, or about 30% CO2. All right, so of the air that's down there. So that's an awful lot of CO2. The trouble is, we got to get from here up here. So how does that happen? What's the mechanism to do that? Well, one of the most amazing things that I've ever seen is something that God created called soil respiration. This is a mechanism that all of nature uses to get the CO2 out of the ground and up to the plants. So this nice little pretty picture is going to explain how that works. What happens is CO2 is produced in the ground by organisms, and we'll have a little picture again in a minute. Anyway, these organisms are producing 10,000 to 30,000 parts per million of CO2. CO2 is heavier than air, than regular air. It's settled, so it's going to settle down in here. So how does it get up here? Well, it just so happens when a cold front comes through, it's a low pressure area. And when that happens, the air pressure drops and the CO2 is sucked up. All right? And it actually gets sucked out of the air. Not only that, usually with low pressure areas, rain comes down and begins to fill up these air cavities and forces the CO2 up into the canopy here. Then there is actually something called siloing that happens in the plants because of the heating, especially when a high pressure in the sun comes up. It causes a convection thing that literally stirs the air up. Now this is not counting the wind that does it, and brings the CO2 to the underside of the leaves where it can be sucked in. Now there is another little aspect. You have carbon, but you need oxygen to make carbon dioxide. So when the high pressure area comes, it actually forces air, O2, oxygen, which is about 20% of our atmosphere, down into the air from the high pressure area, which then forces out the water so that there's actually room in there for the air. And then the microbes have the oxygen to mix with the carbon to create carbon dioxide, thus the cycle. It's called soil respiration. Now that's kind of simplified because there's a lot of little pieces that work together in that, but that's a simplified thing. My deal is that you see how the atmosphere, the natural changes in our atmosphere from high to low pressure areas affect the production of CO2 and the transportation of CO2 to the plants. Well, if you take a step back from that, you have how does these pressure changes? Well, that's weather. Part of it's caused by what they call the Coriolis effect, by the spinning of the earth that causes your fronts to move through. But there's another aspect of that called the sun and the global electric circuit. And what happens is the radiation from the sun and the ionic winds and stuff, that literally put energy into the system and cause it to circle. And that's where all of this happens. It's a very intricate, very complex thing that happens. And in my mind, only a creator could do something like that. That didn't just happen, but that's the way I think. So, but anyway, that's called the carbon cycle. Now, so how does the CO2 get into the soil in the first place? The short answer is through breaking down plant and animal matter. So in other words, we already know that all plants are made of basically 45% carbon. Guess what? People are too. They're, all animals are made of mostly carbon and water. Okay. So anyway, feeding the work crew is what we need to do, and that's what we're going to be talking about today. So we're looking at one of the ways to feed one of the work crews, which is the biology, your fungus and your bacteria, then break down this organic matter into making CO2. All right. So sugar. We're going to look at putting sugar to feed those microbes. So we're going to put sugar in our dirt. We're going to look at is it beneficial? What actually happens? Does the type of sugar matter? How much should we use, and what is the best way to actually get it in there to apply it? Well, is it beneficial? In a word, yes. But there has to be some caution advised in this. Putting it in must be done right, or you can actually cause harm to your plants. Not only your plants, your soil. And we'll get into that in just a little bit. Okay, so what actually happened? Here's another little picture here. So we've added sucrose, which this is the sugar we're going to be talking about. Sucrose, which is table sugar, is the food source, but not for the plant. The plant itself does not suck up sugar. It doesn't do anything. In fact, actually, it puts out sugar. We'll talk about that in another session when we get to talking about the root systems and stuff. They actually have exhalates that come out that are pure sugar. The plant's main job is to make sugar so it can feed the bottom, so that then later on it can get nutrients out so that it can reproduce. And things happen in that particular order. But the plant, primarily, when we go through, when chlorophyll goes through photosynthesis, it's making sugar. And you can tell how healthy a plant is by how much sugar is in the leaves and stuff. So, but anyway, it feeds the microbes in the soil, and they provide CO2. So they're down here, and we have some sugar, and they come down here and they nom, 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 nom on it. They eat it all up and stuff and create the CO2. And it kind of hangs there until our carbon cycle comes through and pushes it all up here, and then the O2 comes back down. And of course, it helps fund all these little critters in here. Kind of like a GoFundMe page for critters, you know. So. But anyway, so it feeds the soil, the mycobacteria, the microbes are fed. It causes a rapid microbial bloom. So if you put sugar on it right now, you're going to get a lot of microbes out of first. It's a bloom. You want to kind of control this, and we'll talk about that in a second. It temporarily ties up your nitrogen, okay? This is called immobilization. So what happens is when this is going down, it does temporarily tie up your nitrogen. So there's a time to do this when you don't need, your plants don't need the nitrogen. If they are in need of nitrogen, you have to really dial back how much you put on it. So, and eventually it will increase the microbial turnover, which releases nutrients later on. Because what happens is a lot of these nutrients are coming in here, and the microbes are actually saying, yeah, I'm making CO2, but I'm also working with a lot of these nutrients, a lot of these minerals and things in here, and they're kind of being brought up to the surface where the roots can absorb them. So that's part of what happens with the microbes as they begin to do the digestion of the carbon. So, does the type of sugar matter? Yes, it does, okay? Let's look at 3 types of sugar that we could add. And there's some variations on these types of sugar, and we'll kind of talk about them as we go and kind of add in them. So the first one is sucrose, which is table sugar. Sucrose is actually composed of 2 types of sugar, fructose and glucose. Now, fructose is actually a modification of glucose, and that's done and then created in the plant. So they do that. But anyway, so those 2 things, but they basically have fructose with an added on, and it's stuck together and it becomes sucrose. It's slow release and will not easily cause a bacterial bloom. It can if you overdo it, and it's what the plant produces to feed the bacteria. So we kind of figured the plant already knows what is really needed. God done created this. In fact, actually, where does our sucrose come from? Most of it comes from the sap of sugarcane or sugar beets. Sometimes corn, but corn is actually a little bit different. Anyway, so fructose. High fructose corn syrup, honey, and fruit juices. All right? It's sometimes called a fruit sugar because fruits have a lot more of it. It's a quicker release that will cause bacterial bloom. This is what fungus feed on, the fungi, the fungi. All right? And bacteria like the glucose and up here and the sucrose, but the fungus like the fructose, which is okay because in sucrose you have both. Alright, so that you actually are able to feed not only the bacteria, but also the fungus that are in the fungi that are in there. So glucose, this is Karo syrup, dextrose, pure glucose. This is what diabetics hate, and sugarholics love, this glucose. So it's a simple sugar, very quick reaction. It can cause a massive microbial bloom. No breakdown required. It can cause bacterial deficit. Oh wow, that's weird. How can it cause a deficit? Isn't that what they eat? Bacteria love this stuff, right? Yep. What happens is they eat all of it, and then there's nothing left. But the next generation of bacteria, they all starve. So you end up with this massive amount. Have you ever seen this, sometimes where they'll have like a bunch of ants or something, and they'll eat all the food in an area. The army ants in South America used to do this. They had these marches, they go through and just wipe out everything. And then they had nothing to eat, so they died back. Well, that's the same thing that happens here. If you get a microbial bloom, they go and eat all of the food, available food in the ground, and then there's nothing to do it. They starve, and they literally starve back too far to where they almost become extinct. It takes a long time for them, because there's no food for them to come back. And so you have to be careful. If you put too much, and that's why you don't use glucose, straight glucose, you don't use kalo syrup or something like that, or these the fructose that's been developed. In fact, if Suzanne was going to be talking about her sugar thing, she'd be really fussing about this one, okay? Because it's the evil fructose, you know. So, but anyway, that's.
If it's separated, I mean, it's just incredible. Do you know if fructose, like that we buy, wasn't manufactured, wasn't discovered how to separate? So the 1950s, 1960s, and 70s is when they figured out a way to mass produce it. And so 1970s it entered food stores.
And now it's in almost everything. Every sweetened drink and stuff like that, and it does some nasty things to your body. So that's going to be next time. Yeah, so anyway, so we get to talking about this. So these are the types of sugar. So we're going to stick here. Now, there's some other ones here that'll contain, because remember, this is made up of these two, but the fact that they have to work at it makes it a little bit easier or slow release. But we can also use things like molasses, okay? You got to watch if you're using something like backstrap molasses, because it can have sulfur in it, or if it's a high sulfur molasses, because you can change the pH of your soil too much with it. So you just got to be careful. You can actually sweeten your soil too much. One of the things we're going to talk about down the road is the pH, changing the pH of our soil. Everybody wants, and the plants and all want this 6.4 pH, which is the super sweet zone for plants. But sometimes it's kind of hard to do that. You can change it, but it'll slowly change back unless you change the microbes in the soil and through the biology of the soil. And we're going to talk about, that's another deal we're going to talk about later on. But anyway, so table sugar, sucrose. It's the breakfast of microbial champions, okay? We take a look at, this is the sucrose, this is the formula for sucrose, C12H22O11. Wow, and that was those first three things, right? Carbon, oxygen, hydrogen. Isn't that amazing that that's what the plant's mostly made of, and that's what sugar is mostly made of. So now, getting that into the plant, that's where the microbes come in handy. So we've got to feed them. All right, so when and how much? Timing and the amount of sugar is very important. Application at the wrong time can actually harm your plant or soil, and too heavy of an application can also harm the soil or the plant. So, one of the ways that in the research I've done, and this is actually how I did it to start off with, was to take at the end of the season, your growing season, you picked all your plants and stuff, and you take the biological matter that's on top, like the old stalks and stuff like that, and shred them up, or chop them up, or whatever. If you just cut them and drop them, it takes a little longer. So what you do is you make a mulch out of them. You put it down, you put this mulch in it, and then if you're going to put a cover crop, which I recommend, you mix those seeds in it, then you do your liquid sugar compound over the top of it. And this is at the time at which you actually would do that, or they're about at the end of the season, okay? Then you let it do its magic, and what will happen is it will actually create a microbial bloom, but a controlled one, inside this organic matter, and break it down so that it's now into a form that can be used by the plants. And as these plants grow, they'll actually use that, okay? So the idea is don't put too much. So what we're going to do is this is how much you would put per 100 square feet, doing it in that method, and doing it using this method here, okay? So you got 2 or 3 inches of shredded plant matter, mulch, whatever, you know. Can even be some green compost, some old, not quite completely compost you put a half to 1 ounce of radish seeds. Now the reason I have it as radish seeds, what I use for this stage is I use a daikon radish, which has a long taproot, which actually goes down into the ground and does several things. It creates air spaces in that ground when it decomposes, but it also, it's a penetrating root that sucks up minerals and brings the minerals from down in the ground up to the top. Then I also use winter peas, and they can be pretty much anything. There's an Australian winter pea you can use. Some of those little peas you were talking about actually might work good, I don't know. And there are 2 to 3 ounces of that. So those are what I spread over 100 feet. And then the spray itself is I use 1 to 2 gallons of water, 2 to 4 teaspoons of sugar or low sulfur molasses.
That's tablespoons. TDS.
Oh, tablespoons, yeah, sorry, not teaspoons, tablespoons. Yeah, teaspoons are gonna be awful light, they won't like it. If there's a possibility that, and this is in here, you don't have to do this, these two here, but if you're having a lot of brown matter in your compost layer here, put in some fish emulsion or a nitrogen source. Old, good composted chicken manure will work great. In fact, Azure sells you've had some, I've seen you had it, Angela, and I use it, it's some good stuff, okay? And it's composted chicken manure, and they made fertilizer out of it. It's a low number, it's like only like a 4.42 or something, but it's perfect for this. Mix that in. And you also, have you ever heard of C90? C90 is a mineral supplement that you can add to your ground. It's actually made from sea salt. And they take seawater, what they do is they go offshore, like around Baja, California, or someplace where there's not a big current that comes from these industrialized areas. So there's not a lot of industrial contaminant in the water itself. So they take it and desalinize, basically pull the salts out of that. And it has about 90 different minerals that are used. Now you don't use a lot. You use 1 to 2 teaspoons per gallon of water over 100 square feet. So it's not a lot of that in there. This will add in a lot of those minerals. Remember we talked about those trace minerals in there? This is the perfect way to do it. I've been using it for a while and it works well. So anyway, you mix all that, you spray that on top of it. Usually, okay, timing. So we're talking about timing on it. For spring planting, assuming that the end of harvest is in October, November, we're going to apply it right after we harvest the plant removal, ideally in the beginning of November or December in that area time frame. You put your mulch down on your bed that you're going to use. You're getting ready to plant your cover crop for the winter. It can be peas, radishes, whatever. You try to do it, but at least got a good 3 or 4 weeks before hard freezes come. And then so you plant that there, and you spray this application, and you soak it down real good. Then you let it go till January. Now this will allow the microbial bloom to occur, which will have time to stabilize prior to planting in the spring. So you put this on there, we talked about the bacteria is eating the mulch, the glucose that's in there is feeding the fructose that's in there is feeding the mycelium and all of this that's in that. And so it's eating and tearing up and breaking down that plant matter. And then it's also because you have the C90 and the other things in there, it's also putting those nutrients into it. And because you come back with a cover crop, it's mixing it. The peas are pulling nitrogen out of the atmosphere, actually out of the ground, and creating, fixing the nitrogen. And that's our nitrogen series, that's later on. So first application is in October, the end of October, as soon as you got it ready to go at the end of season or at the early November. You pick the last of your harvest in October, mulch and return the remaining plant matter, broadcast the cover crop, and then lightly spray your mixture on it. Second application, December, early January. If you're not using a cover crop, you use the same strength that you had up here. If you're using a cover crop, because it can damage your cover crop, you cut it in half and use it. Okay, so you do those same mixtures for 2 to 4 gallons instead of 1 gallon, or 1 to 2 gallons. So, anyway, the application method. Best application is to basically dissolve your sugar in water. I think we talked about it as the day. If you put just granulated sugar, you got fire ant infestation after that. Okay, so it's better to have it in a liquid form. Just dissolve it in water, it does things, and easier to apply and works a lot better. Alright, so that's pretty much it for right now on using the sugar and the stuff. As you know, if you got questions, we'll ask about it. But what we're going to look at is other ways to increase our carbon, the uptake of it. So God's creation does not work alone, along one path, but on multiple intersecting systems. In the future, we will hopefully be looking at many of these other systems that are essential to growing healthy, tasty food in our gardens. Some of those topics: how do we get the happy ground of 6.4 pH? We'll talk about ways to do that. Balancing nitrogen in the soil. Calcium and magnesium, these are micro royalties. In fact, this one right here, if it's not right, there's a whole chunk of things that go wrong. And then you need this one to help control this one. This is like mama and they're like papa, okay? So, and then the more roots, the better. This one right here it's actually amazing because I've started experimenting with actually keeping what they call green manure on a thing where I have a low cover crop, and I'm literally growing my plants through the cover crop. And because of what these roots do to this system, and by bringing nutrients in and putting oxalates in and bringing the biome up, is I'm seeing amazing results of it. So, and then these are just working titles, so they may actually